This week, we're off to the stars. Yes, today we're going to be asking how might advances in space exploration help us solve some of the biggest infrastructure challenges with AI? And what does the future of machine learning look like in space? This is not science fiction. Google have in fact put out an ambitious moonshot paper that explores running ML infrastructure from space. Today we're going to be breaking down some of the key obstacles that we need to overcome to make this work. Despite skepticism from many media outlets that we are in fact in an AI bubble that will soon crash and burn, the demand for AI is actually not slowing down. And if anything, it's only just picking up pace. So we're going to be taking a deep dive into this paper from Google towards a future space-based, highly scalable AI infrastructure system design. And the authors put it very well. Given AI appears to be a foundational general purpose technology akin to electricity or the steam engine, we should anticipate that its use will continue to broaden across all aspects of human endeavour, from powering the economy to helping tackle some of humanity's greatest challenges. And it can be expected that AI computational needs will grow. So this isn't a small problem. According to the International Energy Agency, and that's the world's data crunching infrastructure, data centers and networks are set to consume as much electricity by 2030 as the entire nation of Japan. Now, you may also have heard some of the more outlandish predictions that if we don't get our act together, the entire US power grid could go offline. Of course, companies are trying to fix this, and in the last 18 months, we've seen some pretty impressive solutions, and we shouldn't underplay these. Prompt caching, using AI to manage the cooling systems in data centers, and of course the auto-routing feature in ChatGPT, and the ability to choose the amount of reasoning power in the API. But in the long run, this may not be enough. This is a classic rebound effect. When a technology becomes more efficient, we don't use less of it, we use it more and in new ways. And the total energy consumption continues to climb. Now, AI expert Ethan Mollick, you know I'm a fan of him, has pointed out that the key bottleneck for scaling AI isn't water for cooling, though of course that's a little bit of an issue. It's more about raw power. So if we're running out on room and power on Earth, where do we go? Well, the answer is of course up into space. So how would AI in space work? Well, this moonshot research paper from Google we mentioned earlier proposes a radical solution. It proposes moving the data centers into space. So the idea is that we'll build a highly scalable AI infrastructure that doesn't use terrestrial resources. So instead of building massive concrete data centers and plugging them into our already strained electricity grid, you launch a new kind of data center. It's a fleet of satellites. So here's how it works based on their design. So the paper proposes launching satellites into a dawn-dusk sun-synchronous orbit. So what does that mean? Well, in plain English, that they are almost never in Earth's shadow. These satellites get nearly continuous, unfiltered sunshine, which a panel in orbit receives up to 8 times the intensity of a solar panel on Earth. So there are no fossil fuels, no greenhouse gases, just pure solar power. Now, one of the exciting features about these satellites is that they won't be running on standard GPUs. Google's paper proposes using their own custom tensor processing units, or TPUs. These are accelerator chips. They're chips that are specifically designed for machine learning. And we'll see, they've already been tested for the harsh environment of space. Now, of course, a single satellite really isn't enough when we're talking about machine learning. You need a supercomputer. The plan then is to have the satellites fly in close proximity to each other in a kind of cluster, so they'd be just hundreds of meters apart. Now, they would be networked together, but not with Wi-Fi, but with free space optics. Basically lasers to create a single high bandwidth, low latency data center in the sky. Now, of course, you may ask the question, what about speed? On Earth, Google's TPUs are connected by a low latency optical inter-chip interconnect. And this is how they function as one giant supercomputer. Now, the problem is, of course, that current satellite links are way too slow. Commercially available ones offer 1 to 100 gigabyte per second, and the Google team need an aggregate bandwidth per link on the order of about 10 terabytes per second. That's 100 to 1,000 times faster than what exists at the moment. So you may ask, well, how are they going to get that speed? Well, they'll solve the latency issue in, I think, the most simplistic way. Of course, they'll just move the satellites closer together. And by drastically reducing the distance, they can use standard commercial off-the-shelf, that's COTS, networking gear. And that's the same stuff used in terrestrial data centers. But of course, you do have a new problem now. That's 81 satellites in a 1 kilometer box, and they're all moving around the Earth. How do you stop them from crashing into each other? Well, I think the paper's answer is again beautifully obvious. They propose using an ML-based flight control mode. So you'll literally have an AI serving as the pilot and the air traffic controller for the entire AI data center. So of course, we'll still need to get our questions to the model and get the answers back. And this will be handled by high bandwidth communication links from the satellite cluster to ground stations on the Earth, which will then relay the data through our existing internet infrastructure. So this solves a host of problems at once. No more greenhouse gas emissions for AI compute, vastly reduced need for cooling, radiating heat, of course, into the vacuum of space is easier than air conditioning a warehouse in Arizona, and no more massive construction costs for data centers. Now, of course, this might sound like a 50-year plan, but despite the enormous challenges, which we will come on to later, it is actually starting to happen. At the start of the month, a SpaceX bandwagon mission launched a satellite for a company called StarCloud, and the payload, well, you guessed it, a NVIDIA H100 GPU, probably the most sought out after AI chip on the planet right now, but don't worry. Not one of our beloved babies just yet. Our H100s are all still safely locked down, being looked after for you to rent and deploy whenever you are ready. So the barrier is already being broken. The proof of concept is literally in orbit above our heads as we speak. We can literally put GPUs in the sky. So let's talk a little bit then about some of the problems we need to overcome to make this work. It's all incredibly exciting, of course, but let's just not understate how complex this is. So two of the massive hurdles we need to overcome to make this a reality then. Well, the first and the most obvious hurdle is the cost of launching rockets. It doesn't really matter if the AI is green in space if you're going to burn 1 trillion tons of kerosene to get it there. So the Google paper's entire premise is based on the idea that this problem is being solved by companies like SpaceX. They performed a learning curve analysis, and they project that launch cost to low Earth orbit, that's an LEO, may fall to less than $200 per kilogram by the mid-2030s. So why is this a magic number? Because at $200 a kilogram, the amortized cost of launching the power generating solar arrays becomes roughly comparable to data center energy costs on Earth, with Starship promising costs well below that. In other words, this is the economic barrier that's poised to be shattered, given the huge advances that have already been made in cost reductions by SpaceX. We've all seen, of course, that reusable rocket that Elon has launched. Well, now we're beginning to see some of the fruits of that labour coming to fruition. Now, another problem is data. As StarCloud's CEO noted, downloading SAR data, that's radar data from space, has been historically a problem because it's very, very big. That's the genius of this plan. You don't actually need to downlink the raw data. By putting the H100 in orbit, you can process it in orbit and only downlink the insight. So let me give a clear example of how this would work. Instead of beaming down terabytes of raw satellite images, as we do now, which would be processed by an LLM on the ground, the TPUs in space would process the image the satellite picks up, and they would just send back a tiny text file that would say something like, found a new wildfire starting at these coordinates. And so that's the beauty, really, of having LLM infrastructure in space, which is that we don't necessarily need to send back these huge files all the time. Now, this brings us to our final point, and I think this is one of the most exciting parts of the AI revolution, which is that AI isn't just going to space to solve its own energy problem. It's the key that's unlocking our next era of space exploration. We're building machines that generate data floods. Let's think about some of the huge advances that have happened in space exploration over the last 18 months. We've had the Vera Rubin Observatory in Chile, which, for example, will scan the entire night sky every few days, and so that will collect 20 terabytes of data every single night. Now, human astronomers can't possibly look at all of that, but of course AI can. In its first 10 hours of data collection, Vera found over 2,000 new asteroids. Now that alone exceeds what many ground-based surveys achieve in a full year. We've also seen the James Webb Space Telescope, which is another perfect example. Its images are of course breathtaking. I'm sure you've seen some of them doing the rounds on the internet, but they are the product of intense computation. Now researchers are now of course using neural networks, not just to denoise and deconstruct some of the raw data from JWST, but they're creating images of moons like Io with clarity that would otherwise be impossible. So AI is being used to classify galaxies, find exoplanets, and even detect gravitational waves in data from other observatories. Now all of this of course requires massive compute and infrastructure, and all of that is because of the huge amount of data we're processing. So we're in this fascinating loop. We need AI of course to explore the universe and to expand our knowledge, but that AI needs so much power that it's forcing us to look to the universe, to the sun and to space as a place to run it. So we shouldn't really be slowing down. We're facing massive challenges, but the solutions are not on the ground. They're up in the sky. So the big question for this week then is, what do you think about the future of ML infrastructure in the sky? Do you think sending GPUs, indeed our TPUs, into space, into satellites, is the way that we are going to solve some of the huge infrastructure challenges that we're going to overcome with AI, and the way that we're really going to push compute and push things to the next level? Or are you a little bit skeptical of this? Do you think that actually we need some more smarter ways to solve some of the issues with energy and compute? Whatever your thoughts, let me know in the comments. I'm always curious about what you think and to have a conversation. And of course, give us a like and a subscribe as well. All of it helps us grow the channel, and I will see you next week.